Good afternoon, everyone. I'm Mathilde Boltenhagen from the University of Paris-Saclay. I'm a PhD student under the supervision of Thomas Chatin and Joseph Cormana. Today, I'm presenting an alignment cost-based classification of log tracing using machine learning. It's a work that has been done with Benjamin Chetiri from the University of Bergen and Laurie Nuber from the University of Lorraine. So the context of this work is conformance checking. So there are organizations that record event logs, and thanks to process mining, they are able to record to discover process models that describe the event log. Conformance checking is a subfield of process mining that aims at verifying the process model from the event log. One of the main criteria in conformance checking is fitness, and it describes how well the recorded behavior has been modeled. We can use alignment to compute fitness. An alignment is a fact to find a run of the process model, which is the closest to a trace that appear in the event log. And we count the number of differences between the run and the trace, and it's similar to the edit distance, and we call it the alignment cost. We say that a trace is fitting if its optimal alignment cost is 0. By computing the alignment cost of all the traces that we have in the event log, we are able to get the fitness of the process model from this event log. In this work, we were wondering if we could use machine learning to predict fitness. So can we use machine learning for fitness prediction? As it is a very first work in this direction, we simplified the problem to a binary classification of the log traces. Is a given trace close to the associated process model? We could use a binary classification that classifies a trace as fitting or non-fitting to the process model. But in order to be more flexible, we decided to use a threshold on the alignment cost. So can we align a given trace for an alignment cost threshold to TAC, where TAC is a given number? So we have the event log, a process model, and an alignment cost threshold, and we want to get a binary classification of the traces which are far from the process model or close to the process model. This relates to some paper of the literature that did some binary classifications of deviant and compliant traces. In some cases, they knew the label of the traces, so they knew if the traces were deviant or compliant. And in other cases, they use the attributes to determine the deviant cases. They use machine learning methods to do the classification. The main difference between their work and ours is that we use a model as a base of the classification. So we can say that we are doing a conformance checking like classification. There are also some process discovery contests that ask the applicants to give a classification of the process instances instead of applying an algorithm or a process model. So this is related to what we are doing. Our binary classification is defined by the following. So we have a process model M, a log L, and a given threshold TAC. And the alignment cost threshold-based classification maps each log trace's sigma of the log to one of the two classes, the positive class or the negative class. A trace is classified as positive if its alignment cost is lower or equal to the given threshold. Otherwise, the trace is classified as negative. For instance, sigma has a cost of 3 and the threshold is 2, then the trace is classified as negative. So the trace is considered as far from the process model. From this classification, we found that we can get a lower bound of the fitness of the process model. The idea is very simple. We see that for the traces that are classified as positive, in the worst case, the alignment cost is at distance. The alignment cost is the threshold of the classification. And for the traces that are classified as negative, the worst case is when the cost is maximal and the fitness is 0. And then we have a lower bound of the fitness for the entire log and this model. I've done the theoretical part of the paper, and now I'm going to talk about the experimentation. So this is a chart that describes the experimental setup, and we are going from left to right. The first step is to create the data set. So we had to learn the alignment cost of the different log that we use. We use different log from the literature that have a lot of trace variance, and we use different models from different miners. And here you can find the median and average of the alignment cost, which is important because we use the alignment cost as threshold to set the label if the traces are positive or negative in our classification. We also created some mock traces, so with the same activities and equivalent length of sequences. The next step is the trace encoding. So we use two kinds of encoding: the bag of words that encodes the frequency of the occurrences of the word that appear in the sequence. So we don't have the order in bag of words, but we also have a word-to-index dictionary encoding in which the sequences of words are represented as sequences of integers. And in that case, we keep the order of the activities. We separated a training and testing data set to learn the classifier and then test it. We used two classifiers, a random forest that uses a bag of words, and a BLSTM, which is a recurrent neural network that can remember from backward and forward of the activities. We did a k-fold cross-validation of 10 folds in order to avoid overfitting. And finally, we did the evaluation step on the testing set and also the mock traces in order to check the accuracy and the binary cross entropy loss. And now I'm going to show you the results. In this table, you can find a line per model, log, and threshold. In this case, we show the threshold, which is the median of the alignment cost. In this column, you can see the fitness of the testing set for the model, so which is the real fitness, and we can compare it to the fitness lower bound of our definition, which is based on the classification. We can see that the difference is high, which is expected because our fitness lower bound is a worst case. But when we compare the predicted fitness lower bound to the exact fitness lower bound, we see that we have a very similar fitness, predicted fitness lower bound to the exact one, which can be explained from the accuracy. So we can see that the accuracy are always high. So we can well predict that a trace is far or not to the process model for the given threshold. Now one may wonder, how can we set this threshold, which numbers, because in this table we put the median of the alignment cost, but what happens when we change the threshold? In this table, we show the result for one log and one model and different thresholds. So of course, when you raise the threshold, then you have more traces that are positive. There are more traces that are close to the model if the threshold is higher. The fitness lower bound rise at for some point, and then it will go down if the case is too worse, because the worst case will be worst. We can see that we have a similar accuracy for negative and positive traces, so we are able to predict well both classes. And there is not much differences between the recurrent neural network and the random forest. For future work, we want to improve our mock data, because one of the reviewers pointed out that we did not compare the random forest and the RNN in the sense that we could use sequences with exactly the same number of activities, but in different order, to see if the random forest will indeed be wrong on the prediction, while the recurrent neural network will predict well this kind of case. Also, what can be good is to understand the classification. So why there are some traces that are far from the model and which one are close to the model. And so we can improve the model, so for model repair. Also, we can go deeper in the prediction. We could predict the trace fitness, which is not a binary classification. And we could also do, for instance, a model sequence neural network that in order to predict the alignment with the model move, log move, and synchronous moves. Thank you for listening, and I'm really glad to answer to your questions.
Okay, thank you, Matilde. There is a question. And Anne Gay is asking you, what is the major benefit to classify instead of using the classical conformal checking that is implemented in the system and looking at the fitness?
Okay, so alignment are quite costly to be computed in some cases. For instance, when a trace is very far from the process model, or if a process model is very complex with many nodes, it can be costly to compute alignments. And we can imagine some situation with a web application, which is a streaming application, for instance, and you want to have very fast results, even if there is an error rate. We want to have very fast results. So we can use this approximation, which is a prediction which is simplified from the real alignment, but can be useful when we want quick answer.
Any other question?
And also, I just want to add something. And also, it can be interesting to see, because we don't have much work in that direction in the conformance checking prediction. We don't have much work, so it's also interesting for research.
Okay. Any other comment? There is another comment. In real life situation, how do you ensure that also the negative trace are enclosed in the training set?
So you mean the mock traces, the fake traces?
Because you have a training phase. So I think the question is how you can guarantee that also the negative examples the negative traces are included in the training set.
So I verified that every traces that I test after the training weren't in the training set. So I don't know if
I think it was connected to the real life application. When you are constructing a training set with some traces and you don't know a priori which trace are conformant and which not. I suppose this is the question, but clearly the Jari can provide more details.
I'm not sure I understood. So there are negative traces which are...
I don't know if I correctly interpreted the question. Jari, are you able to speak directly?
Yes, can you hear me?
Yes.
Yes.
Yeah, yes, you corrected, interpreted it correctly. So in a real life situation, your process will not have, ideally not have a lot of non-conforming behavior in your event log.
Indeed.
So if you are training your classifier on a really on a biased data set with a lot of conforming behavior, so how can you fix that?
Okay, so I see what you mean. So I guess that the process model algorithm are not so good to have every trace that are perfectly fitting. So you could set a threshold which is quite low in order to... Oh, no, sorry. Now I understood better the question. So maybe giving some traces that we know that are deviant can help for this problem.
Probably
but we did not do that, but...
can be imbalanced, is this?
Sorry?
Probably the issue is that the training set can be imbalanced because you have a few examples of the negative case and a lot of examples of the positive case. So the problem is that how you perform the learning to be more robust to this imbalanced condition, or if you take into account this aspect in this correction?
No, we did not take this in account, but I think we could shuffle the activities and verify that is not compliant to the process, the business process, and put a label as negative, for instance. But maybe indeed we will not have enough cases. I don't know.
Okay, I have to stop the discussion. Okay. And thank you for the presentation. Thanks. We have a break now.